That's the right one. I got the external one. Finally. So now we'll do a change from the automotive part to the industrial part. I want to showcase our testbed today. We've already been presenting it a couple of times now, actually 2 weeks ago in Pilsen. So me and my colleagues have been working on a funding project the last few months. We started out around 2 years ago now. The main topic actually wasn't anywhere near industrial or automotive. The main topic actually was intrusion detection systems. So the main part was to build detection systems for network systems, for host-based systems, and to build an agent that can test and verify CVEs or vulnerabilities in network. So it can actually interact with the network at hand. So why build a testbed in the first place? So the issue we had, which is quite typical for machine learning systems, we didn't have any data. We found network data, which wasn't very good from a qualitative point of view. We had, for the host-based implementations, requirement to actually run code on some industrial devices, because our project has a focus on industrial systems and network systems close to critical infrastructure. So actually building something or actually getting the data off these devices was a bit of a hassle, since we usually don't get access to the devices themselves. We require licenses. We would have to buy the devices, set these up, build applications that are downscaled to some physical process, and then actually run our measurements to get the data off for the machine learning part. So all in all, we would need access to a network. We would need access to the industrial devices like PLCs, industrial routers, or similar machines. And we would also need some sort of setup that is flexible enough to actually build the agent part that scans the network. So we can actually plug it in somewhere, let it test, change the network, and get data off of it. So our initial goal was to find data, which we couldn't do. So the next step was maybe we could try and build a similar setup. Typically, if you think of a testbed, you will see these physical ones like the giant facilities that they have in England. And I think Augsburg also has a really big one, which is basically a scaled down version of some industrial process, chemical process, whatsoever. So starting from there, we tried to build one ourselves, which is where our research testbed MOTRA comes into play. So we wanted to research attacks on industrial devices and industrial protocols. And from there, we basically started looking for industrial protocols that you can actually test and use. So as I said before, the main issue was if you want to get actual devices running, we would need to buy these, or we would need to get some licenses from the major companies like Siemens, Phoenix, whatsoever, to actually get code so we can work on this stuff. So we're looking at the literature at this time for available protocols that are suitable for our use case. And it turns out most of the stuff that's been open sourced, like Modbus, some versions of Profinet, have already been tested very extensively. So in our case, this meant that there really wasn't anything to do on these protocols. So we started to look further on what other testbeds did, and after some time we came over OPC-UA, which for some reason hasn't been used a lot in actual testbed implementations. So we thought, okay, maybe we could set this up, try a few implementations, try if we could find some bugs, or try if we could replicate some bugs, and use this for our data generation. So OPC-UA, as it stands, is the follow-up of OPC-DA or OPC Classic. It's an open standard, so actually the whole documents are online. You can go check them out. You can check the different layers of the protocol, which you can see here. This is the introduction from UA automation. It has quite a lot of features, which is nice for us for testing, because we actually can test a bunch of stuff. What is also very nice about the foundation, you have tools from the foundation for testing. You have tools for building applications really quickly. And most importantly, we have reference stacks, which are actually used in the industry. The next part that is really interesting is the core stack. since it's made for different platforms and different use cases. It's cross-platform. And since the open standard is freely available, there's lots of different implementations available for embedded targets, for desktop targets, and for server targets. So in our use case, we could actually use the available ones on GitHub for testing. We port these to our testbed and use these as they are for testing. Another interesting part is the object model and the service model, which is, if you can see it, probably the part up here most of the time. So if you get the default OPCOA stack, you will get a set of definitions to build data types. So the nice part about the protocol is if you send data to a device and you get an answer back, you will not only get the raw data back, you will actually get the node and the semantic information back. So you can interpret all the types, all the underlying information and all the stuff, which is nice because it plays well with in-between devices. So if you have embedded devices, desktop devices, and server devices, they're basically to some extent plug and play. So this is really nice because the foundation also offers tools to build these sort of object models. The companion models are actually industry standardized models that are published by the foundation on GitHub. So you can actually take all this stuff, build an application, and throw it on the servers and have it run. It doesn't have a backend that is actually working, but the exposed part over the network, the application model, and the stack will actually be the same for all devices. Then the next interesting part, at least for us, is the extensions. We have extensions for device discovery on the network, which we're currently testing to some extent. We have a lot of certificate management functions, and we have credential management functions, which is nice. These can be extended on top of servers or on top of specialized discovery servers. So these can be integrated into the testbed. And then we have different security architecture and transport options, which is what we can see down here, because OPC isn't layered on top of a single protocol. It's actually a set of rules layered on top of different transport protocols, which we'll see later. So how did we start out? Initially, we started by building the core server versions, which is the most interesting part for us because these we can attack and we can put this into our testbed as single devices. So first off, we started porting some of the available server implementations to Docker, have these run in the testbed, run a few tests, and then we wanted to look, okay, can we scale it up? Can we get the whole thing more flexible? So at the end of the day, we not only have a single node in the testbed, but a couple of nodes, couple of clients, services that we can run against each other. So it turns out the nice part with the core stacks is you can actually automate the entire build process. As I said earlier, we have the companion specifications, which are basically giant XML models. These are descriptions of the nodes. These are descriptions how nodes reference other nodes, how nodes reference data types, and all that sort of stuff. And we can actually take these specifications, load these into the model builder, and build our own models for applications. Basically, what we did at this point is build the application models for our simulation, which is a relatively simple water tank with some valves and some sensors for a chemical process. And we can upload these models to our GitHub or to the core stack repository and put these in together with the ported versions of the different stacks that we had available. Another thing is that we put the different build configurations, extensions, and other configurations that we had for testing into the GitHub repository. And once we had all of these ready, we added additional ported versions of the OPCOA stacks to include some commonly known CVEs, which we found online, which really meant just backporting the existing versions to some earlier version, load the models in, and push these to GitHub. So at the end of the day, we have our set of ported versions, which I think are around 12 or 14 at this time. We have the object models, which is basically a mock-up of some OPCOA application that we can plug our simulations into, and some generic configuration options. And once we throw all of these into Docker, we can build a reference image This is what we will actually deploy later in our testbed. So after this step, we have this set of images. We can start them on any device, like a laptop. Industrial devices offer Docker support these days, like the recent Siemens PLCs or the recent Phoenix PLCs. And what we are currently doing is basically testing these on Raspberry Pis, similar to the HydroProbe. Because these are the closest that we have that will go to that will come to the embedded targets that we usually saw at some of our operators. So as a nice side effect of building these images inside Docker, we can run this simulation as part of the internal Docker network. So from the outside, you will see the OPC-UA servers or the OPC-UA services. And from the inside, you can plug in any sort of simulation clients to feed data into, to hook methods or any service calls into, and to extend basically what the mock-up devices can do. So the nice part about this is for the OPC-UA servers, since the application model basically describes what the entire device will do from the outside, because if you browse the nodes, you will see the entire address space. Once we had the object model ready, we can switch different versions of the OPC-UA stacks, put in the same model, and we basically have the same device, just under a different server, but with different vulnerabilities. So for our data generation, we could actually go, switch up the servers, run a few tests, and see how the entire thing behaves. A nice bonus of this is we can actually scale it up and down really easily. So the next step from there, once we had the servers ready, was to start building a component library. This step basically meant we looked at the entire standard, how it is clustered. We have the core components for communication, like server client and pub sub, and started to check out, okay, are there other components we can implement? Are there other services we can implement? And this is roughly the setup that we have right now. We are still porting some of the discovery services and the global services. But mainly on the left side, we have our server or our communication components, which are basically Docker images. We have the discovery and the global services, which are part of the extensions from OPC-UA. And we added some custom services like databases, web servers for updates, for uploading files and other stuff, so we can add additional CVEs and vulnerabilities to our testbed. We ported these into Docker images. So these are basically building blocks. We can run these in parallel, expose these services for testing, and use Docker or any other system like a container runtime to basically link the resources. For example, if you have certificates enabled, you can share the certificate storage between the containers, you can share resources between the containers, or disable the network isolation between the containers. So you can actually test these from the outside, but you have different components running in different Docker containers. So from there, how does this setup actually work? Currently, we basically have a base image. This can be pulled from GitHub. These are regular Docker files. You can customize these. We can add some additional device configuration, either by the node set, by the object model. We can load in into the server a custom object model. We can extend the existing object models and just have it run some other device. We can get these object models from the vendors. For example, if you go to Siemens, for some devices or for some industries, they actually have ready versions of these models which you can download. So you can put these into one of the devices. Then you can either build it locally or put the entire configuration on Git. And then you can run the entire thing using Docker, or in our case, what we tested is with Compose. The nice thing is with Docker Compose in the most recent versions, you can actually give it a repository or a Git repository somewhere, and we'll actually pull in all the data that it requires. For this, we used named contexts, which is basically a way of telling Docker where to fetch the files during the build steps. And so this way we added different configuration options. We added the base images over Git, And at the end of the day, you basically only need one text file to describe how your application stack looks. And then you can build different services and have them run in parallel. And basically link this up just over the compose specification. Okay, so now the next part, how can we actually test these devices? Currently for the data generation part, because for the machine learning side, we will need the data in the long run. We have started packaging some available tools, regular scanners, some known exploits we found on GitHub and other stuff. Basically put this into a container and set these up. We have some existing exploits for OPC UA that have been published by Clarity a while ago. They actually built an entire testing framework, which is pretty nice, also for testing and debugging. The only issue is all they did was basically wrap their findings in a nice Python script so you can test the different servers on some of the vulnerabilities they found. It's really hard to actually customize these, so you can do tests on existing servers, but you can't really customize the tests on some unknown target or some new server version. So at this point we thought, okay, maybe we could try automating this using Scapy. As you know, there's no port or no really working version of Scapy for OPC UA. So we thought after just spending this much time on the protocol, we'll give it a try. So for this we will have a very quick introduction to UPC. The interesting part about OPC, or the one that we're focusing on at least, is this side here. This is the client-server side. So we have the protocol layer. We have a set of services that we can call as part of OPC UA, which is basically start a session, read data, write data. And everything that's on top of this layer is basically the information model. It's the data that we load into the server that is the actual implementation, or the actual application that we want to run. For example, a sensor having some data nodes. For the most part, most industrial devices will run over the default binary protocol, which is basically a layer on top of TCP. It adds a small portion of transport protocol, which is built into OPC UA. Then you have a security layer, which we ignored because it took too much time to implement. And then you basically have the encoding layer, which is just basically take the nodes, take the IDs, and put all the data on the wire. So with the basic TCP model, which works for most devices, we started to rebuild some of the exploits that we found that worked in our testbed from Clarity, and tried building a working dissector. So the basic message structure is really simple. We have a message header, which is basically 3 fields of the transport protocol, which is a message type, a field for when to chunk the messages as part of the transport layer, which is basically just split the messages up to handle different types of transport media, which OPC also does by itself. And then you just have the message size. This is basically the first part, which sits on top of TCP. Then you have the security header, which in the most simplest configuration basically just sends the certificates and some additional info like server nonsense stuff, which we will ignore. And then we have a sequence header, which is basically the IDs of the sessions we are trying to allocate and the IDs of the user sessions, which we are trying to connect. On top of this, we have the service ID, which is basically just a single ID or a single node as part of the address space, which tells the server what to do. And from there, it's really just payload. So to build these in Scapy, it's basically really simple. We have the binary protocol. The first 3 messages are the transport layer messages. The error close, secure channel, and secure conversation is basically already the security layer. What they did in OPC UA is these layer from the transport protocol and from the security protocol basically have some overlap. So we can just throw them together, which works really nicely. Then we have the selector for the session, or for the service object that we actually want to call on the server. And from there, it's basically the different requests and response messages. So, quick example. These are 2 of the simplest exploits that we found for OPC UA. These are both DOS type. The first one is a chunking attack. This is basically a fault in the transport layer. As we heard earlier, we have the initial fields of OPC-UA, which is the message type. It's a field to chunk messages or not, basically to tell the server, okay, there is more messages coming for this security session. You need to put these together and decrypt these. And the last one was the message size. So as it turns out, many of the initial versions of the OPC-UA protocol actually had an issue where they didn't check when the packets end. So you could just build a session, send the first packet, and then basically just send gigabyte-wise of payload, just by setting the chunking flag. And yeah, this overruns the memory and basically takes down the entire device. This wasn't really super useful. So the next one is actually a bit harder to implement because for this one we actually have to interact with the server, set up a session, and actually read nodes and create subscriptions for the nodes. So in theory, if you create a subscription, every time you connect, you will get notifications if data changes. So this is part of the subscription models. You connect to the server and you will get feedback from the server if something happens. What you can do in this regard, which is basically what is happening here, you connect the transport layer, you build a user session, and from here you browse nodes and you create subscriptions and tell the server you want to monitor these subscriptions. What they forgot in this case was the garbage collections, because you could just recreate the same subscriptions over and over, which is super slow, but it works to take down the memory of the server to some extent. So what we finished in the last few weeks for the OPC-UA part were some of the base services. So we can browse the discovery endpoints, we can open secure channels and open user sessions, we can read nodes, we can browse these nodes, and for the last exploits we had to add the subscription and monitoring part. So with this we can do basic sessions, we can read nodes and values, and can read most of the discovery endpoints. So far the dissecting part works. Crafting is still a work in progress. It's not really finished. But for the transport protocol and for parts of the security protocol, it's enough. So this would work for very simple exploits, but other than this, security is still a very big to-do. So, any questions?
Thank you very much. So, who has some questions about OT security?
It's not about, I don't know anything about the protocol, but I use Docker quite a bit. And what is the network layer you're using? Is it like MAC VLAN to get actually direct access to the services you implemented? Because you said it's just transported over IP in the end. Or is it like the normal Docker where you map a port into internal?
Currently, we're just using the normal Docker because for the exploits that we found for OPC, it's the easiest one, and it doesn't really require the device to actually run on the outside port. So we use the default settings here. Yeah.
Okay. Thanks.
Thank you.
You were mentioning that there are ways this protocol, I don't know anything about this protocol, but you were mentioning that it can also contain semantic information about the data that is sent. Mm-hmm. Does that mean that the packet are describing the fields that are contained, and is it possible? Are you doing dissecting of those? Like, are you creating dynamically classes with dynamic fields? Like, how are you handling that?
So how OPC-UA handles this is basically from the base model. You will get a set of base definitions which I implemented as part of the port, which describe the base data types, like how to interpret the string data, how to interpret double data, all of these things. And when you request a node, it will actually send you back all of the semantic information. So what's the type of the node, in how the relation is as part of the layer model. So you have namespaces, these are numbered. So you actually get back the number of the namespace, where the node lives. So if you go up in the higher layers for the companion specifications and the vendor-specific stuff, you actually need to have the model to know which node you're requesting. But you can browse the address space and get the reference information back of which node type actually references which data type and where it lives in the address space.
So you could make a scanner that scans the entire model even if you don't have it, or?
Yeah, you can. You can. There are tools that basically scan the address space, or at least the part that you're allowed to see, because this has also authentication built into it. So you can actually just request the nodes you're allowed to see.
Thank you.
So, any more questions?
So in the beginning you said something about the machine learning part, and I think at one point I missed it. Are you still planning to using it, or?
Yeah, we're still planning to using. So
Scenario, or?
I think I have the. Oh yeah, here's the slides from last time. So currently this is the prototype testbed that we built. It's basically just a water tank where we mix in some chemicals. The plan is to have this set up on our table. Have a device attacking the servers, or for my part the server in the middle, so where the PLC server sits. And I will run my measurements on the central device. So these are the host-based IDS data. Since we're using Docker, we can set up different devices, have different servers run on different locations. So for the network side, we will just plug in either a tab or some other systems to monitor the networking side. And for the agent-based part, we'll actually just include another device that does the testing. But the plan is to have this set up with OPC UA, have some of the exploits running, and basically take the data, which is why we built the entire thing with different software versions of the servers and the different models in the first place. So we can have a rather fixed setup where you can plug in the network taps and our measurement units at different points and have a similar but not identical network every time to run different tests. Because the main problem is about the machine learning part, the data that we found online, at least for the networking part, because for the host-based part we haven't any data, is usually really similar. So if you plug this into a giant network like an LLM or some other stuff of similar size, it's not guaranteed that you actually train it on the data, but on some timing issues for the protocols that you've seen on the setup they used for the data set. Which is why we wanted to use a flexible network to change up the network architecture a little bit, to change up the versions a little bit, and to change up the exploits in between the tests. So we can actually get data that represents the actual network and the actual protocol, but not a single setup.
But the machine learning part, do you want to use it for, I don't know, anomaly detection, or really to create new attacks out of it, or so?
So my part is mostly anomaly detection. For the vulnerability scanner, it would be nice, but for the runtime that we have for the project, we will probably not make it. But the most part, it's anomaly detection, yes.
Thank you for the great presentation. I have a question based upon the question related to machine learning.
Okay.
So you mentioned that the point is to build a data set related to anomaly detection.
Mm-hmm.
Are you planning on building a data set that contains only the normal behavior so that you can flag anomalies based on what the model has learned from the normal distribution? Or you are planning to have a balanced data set that contains both attacks on the networks, on the OT networks?
Yeah, we want to have both.
Both.
We want to have both, yeah. So that's why we set up the vulnerabilities as part of the server implementations.
Yes.
So for part of the Clarity implementations that we're using for the exploits and some others, the idea is currently to build a capture setup, which is basically a scheduler. So we have the attacking node, we have the server, and we basically schedule the measurement part and the attacking part over the network. So we have different attacks, also default stuff like brute force attacks, port scanners and stuff like this, to run over the night. We have some setup that automates this, and basically have the target node and the attacker node monitor what's happening over the network and monitor what's happening at the actual host that we want to get the host data from. So we try to do both at the moment.
Would it be like a flow-based network packets, or you are going to work on like monitoring a sequence of packets per window size?
As far as I know, both. My colleague isn't here today. I think he tested both. He started with flow-based networks, which worked to some extent, but I think he mentioned the more recent versions of the models, like the bigger ones, actually work better if you feed in the flows, not the flows, but the packets directly. So probably both.
Yes. Perfect.
Thank you. Any further questions? Otherwise, we have a coffee break now.